Good evening, ladies and gentlemen. May you all please rise as the procession enters the venue. Thank you. You may be seated.
Good evening. What a great honor to be here. My name is Kanchikan Rajaratnam. I'm the director of the School for Data Science and Computational Thinking. I'll take this opportunity to welcome you to this inaugural lectures. And I would like to recognize certain people in our audience, or in our midst here. Professor Wim de Villiers, the Rector and Vice Chancellor of the Stellenbosch University. Professor Sibusiso Moyo, the DVC for Research, Innovation, and Postgraduate Studies, and Professor Ram Jagannath, who's the DVC for Teaching and Learning, as well as Dean Bertram Fielding, the Dean of Science, as well as esteemed colleagues, friends, and family. I also want to take this opportunity to welcome someone special, not yet Francesco. I want to welcome Monique Labat. Please, Monique, could you stand up? I would like to celebrate you at the same time, Monique. Monique is the wife of Professor Francesco Petruccione. And welcome to you, Professor Francesco Petruccione. It is my honor to welcome you to this inaugural lecture at Stellenbosch University, where we celebrate not only a career of profound academic achievements, but also a pivotal moment in our institution's advancement in quantum science. Professor Petruccione has been at the forefront of quantum technologies, making significant contribution to the field for over decades. His research has shaped new understandings of open quantum systems and machine learning, providing groundbreaking insight that have influenced both the scientific communities and emerging technologies. He has authored over 250 publications and a seminal book, The Theory of Open Quantum Systems. It is widely cited across the globe. But I'm not here to introduce Professor Petruccione. Professor Sibusiso Moyo will do that. Today, we celebrate his leadership in quantum computing, particularly in his role as the director of NITICS, the National Institute for Theoretical and Computational Sciences, and his work in bridging theoretical quantum principles with real applications. As he presents his lecture, The Adjacent Quantum, Bridging Theory and Technology for a Quantum Future, we are reminded of how his innovative research continues to impact both academia and industry, shaping the future of technology. Francesco, we are very proud of you, and we are really happy that you're part of the School for Data Science and Computational Thinking. Thank you. I pass it over to Professor Sibusiso Moyo now. Thank you.
Good, I think it's good evening, right? Good late afternoon or good evening, everyone, and welcome to this inaugural lecture. It gives great pleasure to do the introduction, and I think in this venue where we are, it's good that there's an organ and the talk that is also on adjacent quantum bridging theory and technology for a quantum future. So Professor Francesco Petruccione, of course, is a distinguished physicist and professor with a rich academic history. He commenced his academic journey at the University of Freiburg in Breisgau, Germany, earning his PhD in 1988, followed by the habilitation degree in 1994. In 2004, he accepted a position of Professor of Theoretical Physics at the University of KwaZulu-Natal in Durban, South Africa. His notable roles there included serving as Pro-Vice Chancellor, Big Data and Informatics, and then maybe we can convince the university to have similar positions one day. By 2007, of course, he was then recognized as the South African Research Chair for Quantum Information Processing and Communication. Currently, he holds dual roles as the Director for the National Institute for Theoretical and Computational Sciences, and since May 2022, as a professor of quantum computing in the School of Data Science and Computational Thinking at Stellenbosch University. Professor Petruccione co-leads the Africa-Europe Cluster of Research Excellence in addressing global and African challenges through methods from artificial intelligence, data science, and theoretical and computational thinking, which we now call core AI, together with Professor David, who's based at the University of Uppsala, Sweden. His accolades are numerous. In 2003, he was awarded the prestigious Stella d'Italia honor by the Italian government, so we also call him Professor Sir Francesco Petruccione. Additionally, he is an elected member of the Academy of Sciences of South Africa and a fellow of various esteemed institutions, including the Royal Society of South Africa, the African Academy of Sciences as well. Professor Petruccione's scholarly contributions are profound, with over 250 papers in peer-reviewed scientific journals. Among his publications, the monograph, The Theory of Open Quantum Systems, stands out, garnering more than 10,000 citations and seeing translations in Russian. Moreover, his collaborative work, Maria Schuit, titled Supervised Learning and Quantum Computers, which was published in 2018. This book has been translated also into Japanese with its second edition, Machine Learning with Quantum Computers, released in 2021. He serves currently on the editorial board of several scientific journals, including Open Systems and Information Dynamics, Scientific Reports, and Quantum Machine Learning. I've known Professor Francesco since 2004, and in many ways, he played a big role in supporting historically black and disadvantaged institutions and emerging researchers. For example, this week, he has been supporting Dr. Yazira Ismail and the organizing team for the 26th Congress of the International Commission for Optics, which is taking place on the African continent and at Stellenbosch University for the very first time, with the two female Nobel laureates attending, Professor Anne Luya, who got the Nobel Prize in Physics in 2023, and Professor Danny Strickland, who got the Nobel Prize in 2018. He's a great mentor, tough, but also very kind with a feminine side. He chaired the committee that wrote the National Integrated Cyber Infrastructure System for South Africa with its 3 pillars. And these pillars are the Center for High Performance Computing, the CHPC, which most of you may know, the South African National Research Network, SANREN, which is aimed at providing high-speed connectivity to scientific research and higher education institutions, and it is geared at ensuring the successful participation of South African researchers, of course, in the global knowledge production effort, SANREN, which you probably also all know if you're part of the higher education institution. The other initiative, the other pillar of this is also the Data Intensive Research Initiative of South Africa, DIRISA, that promotes and enables and coordinates a data-intensive research ecosystem in support of national science and strategic priorities. He was instrumental in the formulation of the quantum technology roadmap for South Africa and has worked very closely with the Department of Science and Innovation and the National Research Foundation. And so for this, currently he sits between, his position is shared between the Department of Physics and the School for Data Science and Computational Thinking. He's currently also promoting open science and interdisciplinary research within NITHEX, with over 26 public institutions which are part of the network, of the NITHEX network, also sponsored through the Department of Science and Innovation and the National Research Foundation. So please join me in welcoming Professor Francesco Petruccione to give this lecture. Thank you.
Thank you very much, Sibu and Kancho, for a very kind introduction. Let's see if this works. Yeah, it works. Fantastic. Because we are in a conservatorium, I thought I structure my lecture like opera. Yeah? So it will have an overture, a few acts, and a finale. Yeah? So this is the plan. So let's start, because we don't have much time, with my journey to reach Stellenbosch. Yeah? I grew up in Genova, in northern Italy. Sorry, I need to stay closer to this. Yeah, in northern Italy. But after my matric, I went to study in Freiburg, in Germany, where I spent almost 20 years. Yeah? After which, as was mentioned, I started. I was offered a position at the University of KwaZulu-Natal. In fact, I was offered a position by the University of Natal. There was no university. I arrived, it was University of KwaZulu-Natal, but and now I'm in Stellenbosch. So you see, every 20 years I change. So I will be I will be around for another while. Yeah? And in the next photo, I will start playing golf, because I decided that dying on the golf course is a nice plan. Yeah? So I'm not playing at the moment. Yeah? So this is how it began. Yeah, this on the right is my first paper during my at the beginning of my PhD, and this is a cartoon of one of my fellow students of the time. And you see, if you can read the title, it had nothing to do with quantum physics. Yeah? But just to places in the historical context, yeah? Were the computing hardware of the time. Yeah? On the left, you see my first PC bought with my hard-earned money as a PhD student, and it didn't have a hard drive, because that was too expensive. Yeah? And on the right was the Cray 1 that we had access to, which was the most famous, the fastest supercomputer of the time. Yeah? And here we are today. And this slide I prepared specifically for Professor Mouton, but he's not here. Because I think I'm one of the few academics that has a Thriller index of 1, yeah? Where one paper has explicitly cited in a very nice thriller. Yeah? So that's something that I really enjoyed. Yeah? Unfortunately, the guy who cites the paper dies a few pages later, but that's another story. Yeah? So and now, of course, we have this MacBook Pro, yeah? and we use quantum computers, about which I will tell you something just now. Because I can't assume that all of you are quantum physicists, yeah? In this first act, yeah, I will briefly try to embed what I'm doing in the general system of quantum theory and quantum technology. Yeah? This year marks 100 years that this gentleman, Louis de Broglie, came up with the idea that even matter behaves like a wave. Yeah? You know, we knew from times that photons, light can behave like a particle and a wave, but it was only 100 years ago that Louis de Broglie, in his PhD thesis, yeah, came up with a suggestion that also matter has wave properties. Yeah? And the most paradigmatic experiment that that can be done, and in the 70s, when Richard Feynman draw this sketch in one of his famous textbooks, yeah, it can be done, can be shown that at that time it was just a thought experiment, yeah, that electron can behave like waves and show interference. Yeah? In the meantime, we can actually do the experiment. Yeah? And if you look at, imagine this is the screen behind the two slits, and you detect the electrons, how they arrive. Yeah? It will take a little while, but it will form a beautiful interference pattern like you would imagine to obtain if you just shine light through. I think you can't. It's just a little bit of an awkward setup. But anyway, you can see now it's accelerated a little bit, that slowly an interference pattern appears, and it's just created by particles that have mass and not by water waves, for instance. Yeah? Okay, so quantum mechanics is a little bit different. Yeah? And in order to understand it, there are essentially two rules that you need to know. Yeah? One rule, and essentially it's the rule that replaces the additivity axiom of probability theory. Yeah? At the core of quantum mechanics is a quantity called the probability amplitude, or some people call it the wave function, yeah? Which is roughly the square root of a probability if you want. Yeah? And the two rules are very simple. Yeah? When two events happen in a sequence, you just multiply the probability amplitude. Yeah? When events happen along different paths, there are alternatives, then you add them. Yeah? And the probability is always a square. Yeah? So this is essentially, out of this you can derive probably most of quantum mechanics. And you can derive also ridiculous situation. I showed you here that you can reach one yellow dot from one yellow dot to the other one along two paths, yeah? And those coexist somehow. Yeah? And this is what in quantum mechanics we call the superposition principle. Yeah? And the most famous example is that of the Schrödinger cat, yeah? That can be dead or alive at the same time until you open the box. Okay, I keep going. Yeah? And that can bring people in trouble. Yeah? There is another property of quantum mechanics that Schrödinger himself regarded as the characteristic trait of quantum mechanics, that is entanglement. Yeah? And entanglement, it what makes quantum mechanics, and I will try to explain it in the next slide, a non-local theory. Einstein didn't like it at all, yeah? And there was big discussion even in the New York Times against this point of view. Yeah? So let me try to explain to you what entanglement is. And instead of having just one cat in a box, we have two cats in two boxes. Yeah? So instead of calling them alive and dead, let's call them up and down cat. Yeah? For some reason, quantum mechanically, the two cases where you have two up cats in the two boxes and two down cats in the two boxes are a little bit boring. Yeah, so let's focus on the case where you have just in one box an up cat and the other one the opposite. Yeah? And entanglement is a strong correlation that is much stronger than any classical correlation you can create. And even if you send the two boxes independently from each other, far, far away, and you open the one box and the cat is up, in the other box the cat will be down. Yeah? So this is a really interesting property of quantum mechanics that has been known since the 30s, but since the 80s we started using it. So it's really a resource of quantum mechanics. And in fact, just 2 years ago, these three gentlemen, Alan Aspect, John Clauser, Anton Zeilinger, got the Nobel Prize for proving that quantum mechanics experimentally is really non-local. That it really has this very strong correlation that we can't reproduce in a classical world. So, just as a little overview, I started the history of quantum mechanics 100 years ago because of the anniversary, and around the same time, Schrödinger came up with his great Schrödinger equation, but it took a long time, at least 20 years, until first applications of quantum mechanics came up. Transistors were invented in the late 40s, after the Second World War. They probably needed them to miniaturize military gadgets. Lasers came up in the 60s, light-emitting diodes also in the 60s. The first microprocessors came out in the 70s, and MRI that we take for granted was only invented around in the early beginning of the 80s. And this is to show you that, let's call the period till 1925-30 the first quantum revolution. It has been instrumental for our third industrial revolution, with a gap of maybe 20, 30 years, from finding the fundamental equation that describes atomic matter to building PCs. It took a while. And at the moment, we are at the edge of a similar development. Before I come to quantum technology, I need to show you something else. So I finished the history here in the 80s. And at that time, something really fundamental happened. Thanks to this gentleman, Hans Timmer, who also got the Nobel Prize eventually, we were able for the first time to observe single atoms. Until the 80s, it was just a thought experiment. We knew how to describe them, but nobody had ever seen one. And in this experiment, you could really see here when the signal goes from 1,900 to down to 0, a photon is emitted from one single atom and reabsorbed. So this was a breakthrough in the 80s. And it took another 40 years or 30 years until Serge Haroche and David Weiland got the Nobel Prize for showing us how to manipulate single quantum particles. That also happened in the end of the 80s, 90s or so. So until then, nobody had ever seen a single atom, and nobody had ever manipulated a single atom. And this was very important because it required also to start thinking how to describe these single quantum particles. Typically, the quantum mechanics that we teach in typical third-year course just describe closed systems. So the quantum system alone in the universe, and everything is very nice. The dynamics, very nice. Oscillatory physicists like to call it unitary evolution, but essentially everything is very nice. In reality, we don't have closed system because everything reacts with everything. Even when the moment an atom emits a photon, it becomes open because the photon goes somewhere. So we need to include where the photon goes in the description. And I spent a lot of time studying these open quantum systems. And two properties that emerge the moment you describe open systems, which are dissipation and decoherence. In this typical closed system approach, energy is conserved, there is no dissipation, everything stays coherent forever. But in reality, it's different. The dissipation and the coherence is a kind of special dissipation acting at much faster time scales has essentially the same effect. So the same effect of this Rabi oscillation in an open system will be damped and eventually vanish. Dissipation and decoherence have very interesting property, yeah? Because on one side, they can be very useful. Yeah? MRI wouldn't work without dissipation and decoherence. Yeah? If you want to do laser cooling, this is another technical thing that also led to a Nobel Prize. It's an essential ingredient. Yeah? Some people believe that to understand quantum gravity, quantum measurement, quantum cosmology, you need to couple quantum mechanics, the coherence with the theory of general relativity. But if you want to build quantum computers, they're the worst enemy because quantum computers exploit this unitary, coherent, oscillatory motion of closed quantum systems. Yeah? And the other problem that open system help us resolve is that of the transition between the quantum and the classical world. We're all made out of atoms, yeah? But this disk is solid, yeah? And it's also made out of atoms. So there must be a mechanism that describes the transition from the quantum coherent world to the classical Newtonian world, yeah? And the coherence is one of the candidates to describe that. Now, this is the most technical. This and the next one are the two most technical slides. So you're welcome to have a little nap. You know, what we want to do is we want to describe single quantum systems. Yeah? Before we do that, the canonical description is that, which is sort of indicated in the green box there of the left, that a quantum system that has many components is usually described by a mixed state of many spooky functions, yeah? Each of them with certain probability. Yeah? So the technical tool that we use to describe them is the density matrix, yeah? Which is a sum of all the possible states with the probability of being in one of those. Yeah? And what the theory of open quantum system does is it considers the total system evolving unitarily according to the Schrödinger equation, and then you try to find simplified dynamics that shows you how the reduced system, the yellow blob, yeah, evolves without having to take into account explicitly the environment. Yeah? But this gives you a statistical approach. Yeah? What you want, and this is one of the probably nicest things that I've done, is to show that you can really describe individual quantum systems by introducing stochastic processes in the space in which this quantum gadget operates, which is called the Hilbert space, so that you can replace the Schrödinger equation by a stochastic differential equation. Yes, where you see that the n is something that can be 0 and 1, and when the photon comes in, it's 1, and when the photon goes out, it's 0, or something like that. Yeah? So this was something very, very interesting, and probably the reason why that famous book that was mentioned was also. Yeah? If this sounds all too Greek to you, some people put it in Russian. Yeah? Now, let me have a sip of water. I promised applications, yeah? And one thing that we came up with around 10 years ago was a new type of quantum walk. Yeah? You know, the standard quantum walks are described by Gaussian processes, yeah? the bell curve kind of diffusion. Yeah? But in this open quantum world, you can map with quantum walks that look completely different. Yeah? Where you see you have a combination of deterministic component and Gaussian packages and so on and so forth. And the trick is that your walker jumps from one open system to the other one. Yeah? And that opened up a lot of useful things, and, and it turned out to be something that many people jumped on and developed further. Yeah? Another thing that was nice, you know, I told you the coherence is usually the mechanism that kills the coherence and makes quantum things classical. Yeah? But if you tune it in the right way, you can show that it can help assist in the transport, for instance, of electrons in a system. Yeah? Here's just a simple example with a two-level system with a dimer. Yeah? And this can have profound implications, as I might show you later. For instance, in quantum quantum effects in biological systems. So everything has, as usual, two sides. It can kill coherence, but it can also enhance certain environmental effects, like transport. Not everything, usually, intuitively, we live in a Markovian world. Just the past doesn't matter. In order to predict the next step, you look at where I am now and you do a step. But there are systems where the history matters. And technically, we call them non-Markovian processes, and in quantum physics, there are similar processes as well, where the system of interest has a memory. And that makes the whole description a little bit more complicated. And recently, with who is somewhere here in the audience, we proposed this kind of generalized theory where the system, instead of interacting with the whole environment, interacts with some pseudo-modes, which in turn interact with an environment, and that leads to a very nice approach to do something analytically and have new tools to describe this kind of systems. Open quantum systems, because we have this opportunity now to manipulate single quantum objects, we can also try to do quantum machines out of them. And it turns out that if you do a kind of a quantum version, for instance, of the Otto cycle, kind of a quantum car engine, if you want, you can increase the efficiency much more than you would expect normally. With a little bit of tricks, but in principle you can increase the efficiency of engines at a quantum level. We rely more and more on solar energy, so batteries become more and more important, and quantum batteries also show that they have better properties than classical batteries. At the moment, it's just a single mini battery, but the principle is there. And integral to this increase of extracting more work from batteries is again entanglement. So these crazy properties of quantum mechanics are really resources that allow us to develop new technologies. And it's just a snapshot of the things that we have done recently, and thank you, Graham, for the nice pictures. Now, let's move to the next act. I promised I would speak about quantum computing, and this is another area, another technology where quantum systems allow us to design computers with completely different architectures from what we use traditionally. And what we have experienced in the last century was that two of the best theories that we have, quantum mechanics and information science, starting merging. And today we have what people call quantum information science. And the three biggest pillars of quantum information science, there are others, are quantum computing, quantum communication, and quantum metrology or sensing. And the overarching vision is to use these three components to build a next generation internet, a quantum internet in which everything is encoded in single photons, for instance. So, people call it now the second quantum revolution because we now use explicitly all the crazy properties, the Schrödinger cats and the entanglements of this world to do things. In metrology, we use it to collect data way more precisely than with any other technology. In communication, we can use it to transport safely data, and this is very important because it's security based on a physical principle, and not on mathematical complexity like in the usual, when you buy something on the internet and you see the lock. So it's really physically proven. In order to be broken, you need to break the laws of physics, which is probably not so easy. And quantum computing promises very fast data processing in certain cases. Sorry. So how does this work? Classically, information science is based on a bit. Some object that is 0 or 1 can be there is a current, there is no current, or something like that. Yeah? The quantum bit is the quantum version of the bit. Yeah? And there is a very simple, maybe we could call it quantization procedure to go from the bit to the qubit, yeah? To the quantum bit that usually is called the qubit. Yeah? And that is to replace the 0 by a two-dimensional vector and the 1 by another two-dimensional vector. Yeah? So you can see optically already that we are living in another world. Yeah? And you can represent this qubit graphically as a vector pointing from the center of the sphere to the surface of the sphere. And every point on the surface of the sphere is a legal qubit value. So you can see with this object qubit, you have many more options. Yeah? And this is what you exploit when you do quantum computing. Let me give you an example, a very simple example of quantum communication. Let's assume you encode your qubit in the polarization state of a single photon. Yeah? And you send it to prepare it. And usually in quantum communication, there is Alice and there is Bob. And if Bob uses the same analyzer as Alice has used to prepare her polarization, Bob receives the same polarized photon, yeah, with spin, with probability 1. Yeah? Now, if Alice sends the same photo and Bob chooses another analyzer, one that is rotated, yeah, the photon doesn't go through. Yeah? But it goes through in one of the other two options that it has. Yeah? So it will be 50% 1 or 50% 0 in this other basis. Yeah? And out of the statistics, you can, Bernard and Brassard in 1994 formulated a first quantum key distribution protocol. Yeah? And the security comes in under the fact that if an eavesdropper tries to steal your photon, yeah, it changes the statistics and you know immediately that something went wrong. Yeah? And back in Durban, we convinced at some stage that the Queen municipality to sponsor the setting up of a secure quantum communication network, which was at the time one of the few existing worldwide. Yeah? And 1 year later, we were able to convince them again to allow us to secure the communication between the Moses Mabhida station and the police through a secure quantum communication link. And at that time, we were really very famous. Yeah? As you can see, with minister, province, municipality, and so on and so forth. And Abdul was the PhD student that helped set up all of this. Yeah, these days, we want to achieve more, yeah, because it turns out that optical communication in fiber, yeah, you can extend only up to a couple of 100 kilometers. Yeah? Maybe the world record might be 400 kilometers, but you can use it in a metropolitan area. Yeah? If you want to connect different parts of the world securely, you need to do it via satellite. Yeah? And we have at the moment a collaboration with a Chinese colleague to try to set up a ground station for one of the Chinese quantum communication satellites. And our photographer knows that we spent several nights on the roof of engineering trying to sort it out. But we will report it later. Yeah? So this is still work in progress. But this is what is coming. Yeah? It's so easy to hack into optical fiber network that people are really seriously looking for alternative. And what you need to keep in mind is that it's not a problem that you might have in 20 years. Yeah? It's a problem that you have now, because I can steal all your encrypted data. I can read them now, but I just leave them in my drawer. And when I have the computer, I read all your secrets. Yeah? So it's a problem that starts already now. Anyway, now, sorry, let me, okay, I'm doing fine. Now I want to move on to one aspect of quantum computing that we do here in Stellenbosch, which is the development of machine learning algorithms to run on these quantum computers. Yeah? But let me, just to put it in perspective, also give you a small timeline of how this thing developed. Yeah? The first idea of using a quantum machine to simulate quantum problems, yeah, was suggested by Richard Feynman in the early 80s. Yeah? There is a famous article and talk of his. Yeah? It took another 5 years until David Deutsch showed on paper, yeah, that in principle it's possible to manipulate information using quantum objects, yeah? Using qubits. Yeah? And this started, of course, because that was the time where we started using and seeing and observing single quantum particles. Yeah? But it took a long time, yeah, until the mid-90s when Peter Shor came up with a factorization algorithm. Yeah? He could show that on a quantum computer, it's much easier to factorize large integer number. Yeah? And this is exactly what is at the core of our security when we buy something on the internet. The RSA algorithm explicitly uses the fact that it's easy to multiply two numbers, but if I give you a number like this and ask you which two numbers did I multiply, it's a more challenging problem. And quantum computers can do this easily. Yeah? A few years later, Grover came up with another algorithm showing that quantum computers can search in unstructured databases way more efficiently than classical computers. Yeah? So for instance, if you want to find my phone number in a telephone book, you search my name and you find the number. But if I give you 0 to 1, 1, 3, 4, 7, 8, 9, find the name of the person. Yeah? That can take a long time, because if you're unlucky, it's the last one. Yeah? So, but quantumly, we can do it much better. Only around the year 2000, the first experimental realization of something that you might want to call a quantum computer with just a couple of qubits, yeah? Was realized using NMR techniques. Yeah? And a few years later, people managed on such a machine to factorize 15. Yeah, so let's find out that 15 is 3 times 5. Yeah? But you have to start somewhere. Yeah? 10 years ago, quantum error correction was demonstrated, which is really important because even quantum computers have errors, yeah? and you need a system to correct the errors that come along, so we know how to do that as well. And 5 years ago, Google claimed to have reached quantum supremacy, yeah? To have solved on a quantum computer with 60-odd qubits, a problem that would take years to solve on a conventional machine. Yeah, so this is more or less where we are. Let's move on without entering in technicality. I just want to show you the basic ideas of how to do machine learning on a quantum computer. Because we are at the intersection between classical and quantum, we have to distinguish between 4 cases. Yeah? Our data can be quantum or classical, and our algorithms can be quantum or classical. Yeah? The KCC would be what everybody does when they use ChatGPT. Yeah? It's classical data on a classical computer. At the moment, it's interesting to study the case CQ, yeah, where you have classical data and you want to input them in a quantum computer and solve a problem more efficiently. Yeah? And this is the case that I will discuss now. Yeah? So what are the challenges? Yeah? A typical machine learning algorithm, you have some data set, you have some prediction algorithm, and you make some prediction. Yeah? Quantum machine learning algorithm, you want, of course, the same data set and the same, or if not better, prediction. Yeah? Could be classification or whatever. Yeah? But there are 2 more steps. Yeah? There is the step that we need to do because we want to do it in a quantum way. Yeah? So we need to encode the classical data into a quantum system. Yeah? Then we need to have our quantum algorithm, and then we need to measure the quantum system and read out the classical result. Yeah? So there are 2 more steps involved. Yeah? And it turns out that we can do the quantum prediction algorithm in some cases exponentially faster on a classical machine. But at the moment, the encoding part can be up to 10,000 times slower than just reading data on a GPU. Yeah? So there is still some work to be done there. Back in 2017, we came up with a very nice minimal machine learning algorithm that resembles a little bit the early day quantum computing algorithm, where we could show that just with one gate here called H that creates superposition, you can classify stuff. You can do binary classification. And we did it with Maria and Mark, who was a master student at the time, using a famous iris flowers data set. You can do that. But what this simple system shows you is that you see the classification part is way shorter than the initial state preparation. Yeah? So that is all the effort that you need to do to put the data set into the quantum computer. Yeah? So, and that is a problem that we still have today. Yeah? In the meantime, together with Matt, who is a PhD student in our group, we can also do kind of way more advanced things like the quantum version of convolutional neural networks, where you can see you have again the data encoding part that is slow, and then you have different layers, where you have a kind of a convolution step where you mix up everything, and you have a pooling step where you compress the data. But at the end, you have just a binary decision whether it's a cat or a dog. Yeah? And we did it also for musical signals. That's appropriate for the venue. You can decide whether something is Taylor Swift or rock yeah? on a quantum, if you are interested. Yeah? If you don't know it already yourself. and this, Sibu mentioned that I like to promote open science. Yeah? We have all this software is open source on GitHub, so everybody is welcome to use it and to contribute to it. Yeah? Because in South Africa we have the square kilometer array, we also applied it to data of the SK, and I think Donovan is also here. Yeah, thank you for that. Yeah, and we were able to show that you can classify out of astrophysical data whether a signal is a pulsar or not, and you can do it competitively. Yeah. And if this still sounds big to you, you can have it in Japanese. Okay, and I think it's time to come slowly to an end. No, there is the last little finale, yeah? Just 5 minutes. We are all made out of quantum stuff, yeah? So it's not surprising that also biological systems have lots of quantum effects. And already the fathers of quantum mechanics, like Erwin Schrödinger, published a book in the 40s, What is Life, in which he sort of predicted that in us there must be something like a DNA. Yeah? He called it an aperiodic solid, but he had exactly in mind the idea of a DNA-like structure, which came, of course, way later. Yeah. So, where one very typical case of application of open quantum systems to biology is to understand how birds navigate. Yeah? And one possibility is that somewhere in the birds there is a kind of light induces an electron transfer that creates a singlet and a triple state. Remember the two cats, the two boxes? Yeah. One was the singlet state, one was the triple state. These in turn create some chemistry, yeah, which in turn becomes biology. Yeah? So at the very top is a quantum effect. Yeah? And there are experiments and there's some evidence that something like that might happen in the beak of birds. Yeah? And there's also something also very, very interesting that we've done recently together with Bethany and Omid, and I think they're both here, and if you want to know more, ask them. Yeah? Is to see how this navigation mechanism evolved evolutionarily. Yeah? And you can show that if the birds picked up some isotopes of certain elements, yeah, in the various cryptochromes, yeah, the mechanism works better. Yeah? So there is an evolutionary advantage in optimizing that reaction, yeah? That radical pair reaction. Yeah? Again, the same singlet and triplet story. Yeah? This has also implications. It is also something interesting where, again, Bethany and Omid were involved and others. Yeah? You know, one of my famous PhD students, Adriana Mare, enjoyed so much working with me that she decided to go to Mars. Yeah? But all these effects imply the interaction with a magnetic field, yeah? Even in navigation. Yeah? And, and planets in our solar system have different magnetic fields. It's not the same magnetic field as here. Yeah? So that there might be serious implications for our biochemistry at a quantum level if we live in a planet that has a completely different magnetic field to what we are accustomed to. Yeah? So I'm not in a rush to go to Mars. Yeah? You know, a few years ago, all of us were studying something around COVID, yeah? And we made a very nice model. Usually, you know, if you look at how the spike protein attaches to the receptor, you have a kind of a lock and key mechanism in the hair. Yeah? But it could well be that there are other mechanisms that can describe that as well. Yeah? And there are vibration-assisted kind of tunneling mechanism that work. Yeah? And with a very simple model, we've shown you can identify kind of by analyzing the vibration spectrum, the intrinsic quantities that you might be able to change to make the infection more difficult, essentially with light. Yeah? So, but this is just a very simple model, and hopefully one day we'll be able to do some more. And this is a mechanism that is similar, you know, this vibration-assisted electron transfer argument were first proposed to explain olfaction. Yeah? The standard theory of olfaction is also a lock and key mechanism. Yeah? But, you know, we probably can smell things that evolutionarily we have never smelled before. Yeah? So it's quite unlikely that there is a lock and key mechanism for everything. Yeah? And there are models to explain olfaction in a similar fashion. Yeah? Even the origin of life, there is always a spark that induces some electronic transition of sorts. Yeah? And you know, some people like Miller and Fred did it long ago in the lab, but you know, it would be nice to find a mechanism that could have happened spontaneously just because of a lightning, the presence of some metals somewhere, and some catalytic reaction, and so on and so forth. Yeah? And this is also something that we are looking into. Yeah? So the journey would not be complete if we wouldn't think about, can quantum physics help us understand how our brain works? Yeah? And in the 90s, Roger Penrose, famous physicist, also Nobel Prize laureate, came up with a theory that is called orchestrated objective reduction, in which he claims that in the microtubules there are some coherent quantum effects that have something to do with consciousness. Yeah? And it was quite a speculative idea at the time. Yeah? But you can take a more empirical approach and start to look what quantum effects might happen in our brain. Yeah? And this is something that, again, Bethany spearheaded a few years ago, yeah? And also had to be on the title page on Physics World. Yeah? You can see that, for instance, let me just focus on the second one, the entanglement one. Yeah? People think that there might be molecules in our brain that have the property of storing coherence for long time periods. Yeah? And long means maybe minutes, yeah? Enough to do something in the brain. And these objects are called Posner molecules. Yeah? And in fact, they exist in the mitochondria. Yeah? They are mainly calcium and phosphorus. Yeah? And one can show that under certain conditions, you manage to entangle such Posner molecules or the phosphates in the Posner molecules for sufficiently long time that something interesting could happen. Which is very interesting because there are models of building quantum computers, and people in Australia are trying very hard, that essentially use the same phosphorus, the same approach to build quantum computers on silicon substrate, manipulating and the silicon is dotted with phosphorus, and by manipulating the spin of the phosphorus, they hope to be able to create this kind of entangled state on a chip. Yeah? And it's exactly the same mechanism as here. Yeah? So that coming to an end, I don't know if that will be true or not, but the only thing that we can say for sure about consciousness is that you can solve it in chloroform. Yeah? And that's it. So thank you very much, and I would like to thank Stellenbosch University for the opportunity of being here. I have to thank NITEX, yeah, and all colleagues, students, friends, funding agency, departments, the audience in general, and Monique, who didn't oppose my move to Stellenbosch. So thank you very much.
So good evening, friends. So it is my privilege as a member of the Rectorate to provide a response and then also to hand over a certificate to our professor for having delivered an inaugural lecture. So I'm Wim de Villiers, I'm the Rector and Vice Chancellor. And so what a privilege to have heard this inaugural lecture this evening. And an inaugural lecture is quite a thing in an academic's career, because this is when you profess as to your disciplinary expertise. And I think we can all attest to magnificent disciplinary expertise this evening. It was a tour de force. So thank you very much, Francesco. Just give him another hand of applause. So the title of his talk was The Adjacent Quantum Bridging Theory and Technology for a Quantum Future. So he took us through a fly-through of the history of quantum physics. He showed us quantum computing, and he also showed us quantum machine learning. And I am a physician and a gastroenterologist by training. So I was, of course, particularly piqued and interested in MRI, in the direction of the MRI technology, also laser spectroscopy, and these foray into life sciences and the neurosciences this evening. But he really showed his mastery of this subject. So recently, I visited Manchester for the Times Higher Education Conference. So this is an annual conference of education institutions. There were about 500 attendees, and it was hosted by the University of Manchester. So the host institution always uses this as sort of an opportunity to show off whom they have on their staff, and also who some of their illustrious alumni might be. So University of Manchester, there are two who come to mind. Alan Turing, who was the father of theoretical computer science. He trained at the University of Cambridge and also at Princeton, but then subsequently worked at the University of Manchester, where he also died at the age of 41 there. And then secondly was Ernest Rutherford, the father of nuclear physics, who got a Nobel Prize in 1908, who was also worked at the University of Manchester, and they're very proud of him. Now, Ernest Rutherford, of course, is one of his well-known quotes is that he said, all of science is physics. All the rest is mere stamp collecting. And I must say, having heard this impressive foray in quantum physics and quantum computing and quantum machine learning, I have to grudgingly, as a physician in gastroenterology, yield to Francesco here this evening. So I think what a marvelous lecture. We're so pleased to have him here on our staff for the past 2.5 years. We got him recruited him from UKZN. He set up a Center for Quantum Science and Technology here at Stellenbosch University. He's also relatively recently won the bid for Stellenbosch University to host the National Institute for Theoretical and Computational Science, NITHEX, here at our university. And then he also co-leads the Arua Guild Cluster of Research Excellence. So that's the African Research Universities Alliance, the Arua Guild Cluster of Research Excellence in addressing global and African challenges through methods from artificial intelligence, data science, theoretical, and computational thinking. So I think it is one of the other, so definitely if we talk about Alan Turing and we talk about Ernest Rutherford, we're going to, when we host the THE conference here at Stellenbosch University, I'm going to showcase Francesco here as our communicator for quantum physics and quantum and quantum computing. So the other person that the University of Manchester showcased there was Brian Cox, who's also on there. He's a cosmologist. Some of you may know him as for his radio show and podcasts, and also he gives all sorts of other public appearances as an eminent science communicator and the importance of science communication. And so I was privileged to listen to a lecture of his. And he drew my attention to an essay that Richard Feynman had delivered in 1955 to the American Association of Science, and it was on the value of science. And it's a beautiful lecture and an essay that I really encourage you to read. And it's just maybe the main point of that article is, of all its many values, Feynman said, the greatest must be the freedom to doubt, and the importance of that in all the work that we also do as scientists. So it's a great pleasure for me to congratulate Professor Francesco Petruccione on his outstanding inaugural lecture and to hand over the certificate. Well done.
Colleagues, friends, once again, thank you for being with us. To everybody that has joined us online, thank you for taking time. It's always good to see this type of turnout at an inaugural lecture, because it shows the impact that somebody has, not only in their field and their discipline, but also on people. And if you look at the mixture of people that we have here tonight, it is a career that has impacted many across the years. And Francesco, I don't believe you that the next stage is you playing golf. Seeing you walk around on campus so calmly thinking about what you need to do and how you need to do in your field, I think that is what keeps you going. But once again, thank you. It was a privilege and an honor to listen to you. My name is Bertie Fielding. I'm the Dean of the Faculty of Science, and it is my honor to just do the word of thanks. So firstly, I would like to express our appreciation to the Rectorate members, Professor Wim de Villiers, Professor Moyo, Professor Ramjoganath, for attending this evening. Thank you for hosting us. Professor Wikus van Niekerk, Dean of Engineering, who's attending online. Wikus, once again, thank you for always being available to attend these. Kanshu, Director of the school that hosts. Francesco, thank you for being the host tonight and for just welcoming us here. I would also like to extend our appreciation to Francesco's wife, Monique. There's a saying behind every great man is an even greater woman. Thank you for sharing Francesco with Stellenbosch. But also sharing him with the scientific community. I know being married myself, it's not always easy, but it always helps to have an understanding spouse at home. So thank you from us. To Francesco's extended family, friends, colleagues, academic partners, and collaborations, and then very, very importantly as well, to our students who are attending here tonight in person and also attending online. You are the ones that people like Francesco invest in for a purpose. You are the ones, I believe, that Stellenbosch sees as the future and will make the contributions. And hopefully, this audience tonight, for those of you who attended the Nobel Committee talk last night, hopefully we have a future Nobel laureate in the audience. So keep on dreaming, trust me. Francesco, I think your time is running out, so you really need to do the really significant work now. We heard that it's only awarded to living individuals, so please. Sibu said last night that Stellenbosch needs one. So it's either you or your colleagues in that row, but no pressure. So to everybody, all friends, family, to Francesco's in the audience tonight and online, thank you for just walking the journey with him and for really just being the support to him. Colleagues, we need to say a huge thank you to those people who work behind the scenes to make this what it is. There are snacks outside to those who prepare the snacks and who make sure that we have the snacks. To the photographer, our sound people, thank you so much. But in particular, Latasha from the director's office, Amira and Chuma from the marketing team, Justin from the communications team, and then the old start marker, I think he's outside laying down because he's not feeling 100%. Jonathan Dale, thank you for everything that you do and always making sure that these things run smoothly. We appreciate you. And then finally, once again, Francesco, I think you were a bit modest tonight. You presented your work, but you really did not show us in detail the impact you have across disciplines. And that's why when you look into the audience tonight, you see more than physicists, you see more than scientists. You see biologists, and you see engineers. We've had conversations. And the willingness of Francesco to work with others outside his discipline, I think is what makes Francesco Francesco. So thank you from our faculty as well. We appreciate you. Colleagues, we now invite you all present to join us for light refreshments in the foyer. I ask you to rise, please, as Francesco will lead out the presentation, and then all the procession members will follow him, and then join us for refreshments in the foyer. And once again, safe home, and thank you for your presence here tonight. We appreciate you.